Hi, my name is Qijing Jenny. I'm a final year PhD from UC Berkeley. Today I'm going to present our work called CoDeNet. It is about efficient deployment of input adaptive object detection on embedded FPGAs. I will first cover the motivation for this project. Nowadays, there are many diverse applications at the edge, such as robotics, drones, autonomous vehicles, security cameras, and smartphones. All these applications rely on only a few core computer vision kernels, such as image classification, object detection, and semantic segmentation. So this means if we optimize these kernels well, we can deploy all these applications efficiently on various embedded platforms, including FPGAs. However, there is several challenges. First, many computer vision tasks use large inefficient models and operations. They are solely optimized for accuracy. Besides, embedded devices typically come with limited compute resources and a tight energy budget. And lastly, many applications demand response within certain time constraints. So this imposes real-time requirements on embedded accelerators. In addition, a majority of existing work focuses on accelerating image classification, while object detection have not been adequately studied. And compared to image classification, a major difference of the detection tasks is that they are more sensitive to the spatial variance of objects. The goal of our project is to co-design object detection algorithms and accelerators that satisfy embedded system constraints and fall on the Pareto optimal curve of the accuracy-latency tradeoff. To attain this goal, we first aim to find an efficient operation to support. And deformable convolution was brought to our attention. This operation is introduced to address the need to capture spatial variance of objects and boost the accuracy of the state-of-the-art object detection models. Our friends from the computer vision community told us that adding this operation generally can add 2 points to the accuracy for the state-of-the-art object detection pipelines targeting the COCO dataset. So let's dive into more detail. Deformable convolution is an input adaptive dynamic operation that samples inputs from variable spatial locations. This operation first generates the sampling offsets from the input feature maps, and then use these offsets to sample data again from the same input feature map. This sampling locations vary with different input images and different output locations. As shown in this example, the sampling locations highlighted in red dots are different for different objects of interest in this image, highlighted with green dots. For example, if the focus is the lawn, then the sampling locations are scattered among the grass. And if the focus is the car, then the red dot, which are the sampling locations, are scattered around this car. Besides, this operation can also capture objects with different scales, aspect ratio, and rotation angles. So on the algorithm side, this operation has been shown to be very effective. However, as a hardware person, what we would like to know is that what's its implication on hardware design. So the deformable convolution actually introduced new computation and memory requirements for the offset generation and transfer. It also introduced an irregular input-dependent memory access pattern, which make it hard to reuse input with the common output stationary and row stationary data flow design. So in this work, we're trying to perform step-by-step algorithm hardware code design at the operation level as well as at the network level to design Pareto optimal solutions with the operation for object detection. So here's the original form of the deformable convolution. The offsets are typically floating point values, as the bilinear interpretation is used for offset generation network to make this training process differentiable. For our hardware design, we then preload the weights onto the on-chip buffer and loads the input and offset from the DRAM without spatial reuse in our original baseline design. And the first modification we make is to reduce the operation density from full convolution to depthwise convolution. So in this case, we are able to reduce the total computation required as well as the total parameter size of this operation. The second optimization we perform is to bound the range of this operator. So we limit the offset range to from -8 to +7. This allows us to add a line buffer on the hardware accelerator to buffer the input from the spatial dimension in our accelerator. And next, we're trying to see what is the accuracy when we force the shape of the deformable convolution to a rectangle shape. As opposed to the previous step, it actually increases the accuracy by 0.1 points. And this allows us to enable the parallel loading of fixed number of data in every cycle from VRAM. And in this case, there will be 3 points loaded from the line buffer when we constrain the shape to rectangle in this design. And here is a summary of our twofold co-design approach. First, we select efficient operation to support, which is the input adaptive deformable convolution in this case. To make this operation more hardware friendly with more regular access pattern and more efficient operation, we made several changes to its original form, including bound the range of the offsets, constrain the shape of the offset to be a rectangle, round the offset to integer, and make this operation depthwise. We then co-designed the hardware engine with this efficient operation. We made corresponding hardware modifications to leverage the algorithm co-design features, including use last level cache on the SoC, add line buffers, and allow parallel ports on the SRAM in order to fully exploit the locality and increase the on-chip memory bandwidth. Here we show an application study for the impact of co-design deformable convolution on accuracy of object detection. We first showed that the original 3x3 deformable convolution is more efficient than large convolution kernel that achieves comparable accuracy. For example, the original deformable convolution can achieve higher accuracy compared to a 7x7 convolution, but with 5 times less computation involved. Then we show with our co-design operation, after us performing a series of changes, can achieve still good enough accuracy compared to the original deformable convolution. And this table here shows the inference latency on the co-designed hardware with each modification in the operation. It shows that our hardware achieves 1.36 times speedup for full deformable convolution and 9.76 times speedup for depthwise deformable convolution. And with this co-design methodology, the deformable convolution becomes very close to the original regular convolution in terms of the inferencing latency. In addition to the deformable convolution operation, the design of feature extractor, detection heads, and quantization strategy also significantly impact the accuracy and efficiency of the detection system. And in this part, I'm going to cover how we co-design the detection system together with the co-designed operation. To co-design the object detection systems, we first adopt simple building blocks to reduce the hardware complexity. So building block A and B are the blocks we adopt from ShuffleNet V2 design. Building block C is the upsampling layer with the deformable convolution. It is used to upsample the backbone features, and in the design, the first one-by-one convolution is designed to map input channels to different output channels. The following 3x3 depthwise convolution samples from the previous feature map according to the offset generated by the one-by-one convolution. After that, a 2 times upsampling layer operated by a nearest neighbor kernel is utilized to interpolate the higher resolution features. And this figure shows the overall neural network architecture for object detection. So for the backbone feature extractor, which is the left branch, we chose ShuffleNet V2 design for its efficiency and ease for quantization. Building block A and B together form a shuffle block as shown in this left branch as part of the ShuffleNet V2 feature extractor. For the detection head design on the right side, we use single-stage anchor-free center net to directly predict the center of each object, so we can get rid of the overhead for post-non-maximum suppression processing. We use the anchor-free center net methods to directly predict a Gaussian distribution for object center points over the 2D space for object detection. So as illustrated in this figure, the output of center net detection head includes the center heat map, the object size, and the local offset. And quantization is another critical step towards the efficient deployment of the pre-trained models on GPU and adapted onto FPGA accelerators. For the deformable convolution, quantization comprises 2 parts. The first part is to quantize the corresponding weights and activations as usual. And the second part includes the rounding and bounding of these sampling offsets of the deformable convolution to integer and within certain limits. So compared to the standard convolution, this variable offsets will not significantly change the sensitivity of the network or the allowable quantization bitwidth. And regarding the original fractional offsets, we bound and round them to be integers within the range, as we mentioned in the previous session. With our co-design methodology, we're able to reduce the types of operations to support as well in this accelerator design. Excluding the first layer for the full 3x3 convolution, CoDeNet only consists of the following operations: 1x1 convolution, 3x3 depthwise deformable convolution, quantization, and split, shuffle, and memory concatenation units. And this helps us to greatly simplify the complexity of the control logic and thus save more FPGA resources for the actual computation. We partition the CoDeNet workflow so that the frequently called compute-intensive operations are offloaded to the FPGA accelerator, while the other operations are run by software on the processor side. These operations we choose to accelerate are 1x1 convolution, 3x3 depthwise deformable convolution, and quantization. This slide shows our overall accelerator architecture diagram for supporting a subgraph of 1x1 convolution followed by 3x3 depthwise convolution. To leverage both the data level and the task level parallelism, we design a spatial data flow accelerator engine to execute a subgraph of the CoDeNet at a time, and we store the intermediate output to the DRAM. In this data flow engine, the execution of compute It's determined by the arrival of the data and thus further reduce the overhead of the control. Next, I'm gonna show the final results we got from our co-designed object detection pipeline on an embedded FPGA. We run the Accelerator on the Ultra 96 board with a Xilinx CU3EG FPGA. It comes with 34K LUTs, 41K flip-flops, 216 BRAMs, and 360 DSPs. The table below shows the FPGA resource utilization of our Accelerator. Our Hadlson's implementation uses 100% of the BRAMs and the DSPs on this board. We implemented CoDeNet model in PyTorch, trained it with a pre-trained ShuffleNet V2 backbone feature extractor, and quantized the network to use 8-bit activation and 4-bit weights. We devised several configurations of CoDeNet to facilitate the latency accuracy trade-offs for our final object detection solutions on the embedded FPGAs. And there are 5 different configurations of CoDeNet listed in this table. Compared to the Tiny-YOLO work, our configuration C model can achieve higher accuracy, but its model size is 10 times smaller without quantization and around 80 times smaller with quantization. And this slide shows the latency accuracy trade-off for 5 CoDeNet design points on our embedded FPGA running with 4-bit weights and 8-bit activation. The x-axis shows the inference time in milliseconds for the batch size equals to 1 input, and the y-axis represents the AP50 accuracy on VOC dataset. As shown in this table, compared to the results we got from FinR that targets VOC on the same FPGA platform, our configuration A and B with single batch inference frame rate at 32.2 and 26.9 can achieve both higher accuracy and higher frame rate. So to conclude, in this work, we perform algorithm hardware co-design at the operation level as well as at the network level for the deformable convolution-based object detection pipeline. We co-designed input adaptive network model and achieves high accuracy with very compact model size. And our co-designed hardware can achieve real-time inference speed for input with batch size equals to 1. And overall, this work demonstrates the effectiveness of algorithm hardware co-design methodology. And for the future work, we will plan to train a multitask model with the deformable convolution to reduce the repetitive processing efforts on the backbone design. We're also interested in building an automatic neural network architecture search with this novel operations. So if you have any questions, please feel free to email me at this following email address, and you can view our code at this GitHub link. Thanks for listening to our talk.